All right, so I will share the document with what's going to be on the test. So it's pretty similar to the other stuff. I guess there's feels like there's less story problems on this one than there are the last couple tests.
Sweet.
I don't feel like the initial value problems or the related rates problems got any harder. They're about the same. Derivatives are a little bit more complicated, and the integrals are a little bit more complicated, and the limits are a little more complicated. But and they have proofs. So they have the epsilon delta proof, which can be kind of confusing, and then the definition of a derivative and like the difference quotient. So those are, I guess, so as of like integral and derivative rules, I don't think they're really adding things. It's just explanations about why things work, I think, is what this test is kind of about.
Okay.
All right. So I guess actually, if are there anything you would like to start off with looking at these?
Why don't we just do what you want to cover, and then if I have any more questions.
All right.
If that works for you.
All right, so we'll just start with the derivative problems. So I guess this one, like I said, it's just more like, because they didn't really add any new rules on derivatives, so it's just kind of the problems have a little more algebra in them, I think, and you have to do a little bit more simplification. So one thing that I noticed that would be helpful is like reviewing completing the square again. So let's say we have this 1 over x squared plus 14x plus 65. Oh, that's the wrong problem. What am I thinking? Derivatives. We're on derivatives. We're not there yet. I was looking at the wrong thing. Derivative-wise, okay, so the first one that I thought would be useful is change of base formula. So if we have something like a log of some base, right? If we were to take the derivative of this, we don't really have rules that do just straight log with and kind of this arbitrary base, or this base that doesn't really match what we have. So you can use the change of base formula, which let's just change what this base is. So it basically says we can rewrite this to be a base of the argument. So and over of the base itself. But in this case, since we get to choose what the base is, we're going to choose e. Right, because log base e is natural log. And so basically you can just rewrite this to be a bunch of natural logs, and then it becomes an easier problem. That makes sense?
Okay.
So we can rewrite this to say that this is going to be the natural log of 3x plus 7 over the natural log of 8 using the change of base formula. So then this becomes a much more doable problem, right? Because we didn't have a rule, now we have rules. So we can just separate this one ln 8 because it's a constant. We can just take that out. And then we can just use the ln derivative rule. So it's going to be 1 over the inside function times the derivative, which happens to be 3, right? So we can, and that would be our answer. So but it's not really like a hard problem. It's just remembering that you can do this. There's a lot of stuff in algebra that you can do some cool stuff with algebra that I feel like it's pretty easy to forget that you can do. So I think that's the first one that I noticed with the derivatives that would be helpful. Then the other trick is just the natural log thing again. So if we had something like y is equal to x to the 3x plus x squared, something like this. We can we're going to use natural logs again. We can just take the natural log of both sides.
And the x moves in front, right?
Yeah, and then move the exponents down if we do that. All right. So, and then this would be y. Forgot the y. And then we just use implicit differentiation for this. So this would be 1 over y dy dx, right? 3. And we have to remember that this is in parentheses, so we're going to need to do a product rule here, right? So the derivative of the first, 3 plus 2x times ln x plus 1 over x times 3x plus x squared. That makes sense how we did that? It was kind of fast.
Yeah.
And then we just multiply this y over, multiply this whole function by y, and this will get rid of that on that side. And then this is our problem, and this is our answer, except for we just got to remember that we want it all in x's, so we can go back up and replace this y with x's.
Oh. Okay.
Yeah. And if you really wanted to, you could factor out an x out of this.
Right.
That would be just an x. And then it would all be multiplied by this x to the 3x plus x squared. So they're not super hard problems, but it's just remembering those weird algebraic rules that you haven't seen in a long time that can help you rewrite some of these problems into a more doable calculus form. And so that was kind of the things that I saw that was kind of tricky about the derivatives on this test. Other than that, the chain rule is useful, and making sure you know your inverse tangent, your inverse trig functions, like the derivatives of your inverse trig functions. Those are helpful.
Okay.
So, all right, so that's pretty much it for the derivatives. Integral wise, it's kind of a similar thing where we're not working with really any more rules, but it's just being able to do things algebraically that will help you with your rules. So now we get this one, right? So we have this 1 over x squared plus 14x plus 65, right? Dx. So if we're looking at this integral problem, there's really so we can say, well, u substitution doesn't really work here, right? And it's not really just a general power rule because this is in the denominator, so this is a complete the square problem, and so we'll complete the square real quick. We'll leave a blank space here. We'll have this plus, and we'll move this to the other side. So we'll say that this equals 0, and we'll move this to the other side. So we have this negative 65. Now we can use, so what we're essentially looking for is we want this x plus a squared, right?
Right.
But we're going to just have stuff afterwards, right? To complete our square. And so we're going to take the formula, because if we FOIL this out, this x plus a squared, we get x squared plus 2ax plus a squared, right?
Right.
Well, if we look at this formula, what are we missing? We're just missing this a squared, right?
Right.
But we can use this middle term to find out what this a is. So we can set this 2ax is equal to 14x. And we can say that a is equal to 7, right?
Right.
That makes sense.
Mm-hmm.
So then we can just say that, well, this is going to be 7 squared. And if we do this to one side, we have to do it to both sides.
And we're left with 16.
Yeah, so then we have x plus 7 squared. And then this will be plus 16, because this comes out to be a negative 16 up here, and then we'll add it back over. So there's our square, right? And so now if we come back to our integral problem, I'm going to rewrite this 16 to be 4 squared And then we're going to just simply use inverse tangent here to complete our integral, right? And it's going to be 1 over a, right, if you remember.
Mm-hmm.
So 1 over 4, and then it'll be tangent inverse of u over a, or x plus 7 over 4. And we're going to have this plus c on the end. So just completing the square. So I feel like this problem is more algebra than it is calculus. It's just remembering how to do this. And once you get to the calculus step, it's actually really simple. So
Okay.
that makes sense. Are there any other questions about this problem?
Mm-mm. Yeah, that makes sense.
All right. So the other thing that I noticed, like, it really is just a bunch of algebra rules, but one of the other things that I thought would be worth covering is stuff like this. So when you initially look at this problem, it kind of just looks like a u-sub problem, right? But it's not really, because we have this -8 right here.
Mm-hmm.
And so if we do the u-sub problem as it's written right now, it's not going to work. So the way we get around that is we just rewrite the problem algebraically. So we're just going to split this at the minus sign, right? So,
oh, I see.
and then we're going to have this minus, and I'm actually going to pull this 8 out right now. Right? And now this becomes a much more doable problem, right? Well, this one now is u substitution, and this one is just the inverse sign, right? So we're going to have -8 sine inverse of x of that. So we already know what this one is, right? So now we just have to go through and solve this one. So we can pull this, we can say, yeah, if we wanted to, we can pull this 4 out, but I'll just leave it in there for now. So u is equal to 1 minus x squared, du is equal to minus 2x dx. All right, and then all right, and then we can pull this -2 out, right? And then these x will disappear. And then this, we can rewrite this as u to -1/2. So that'd be u to the 1/2 times 2 times -2, right? That made sense how we got there. I kind of was kind of quick. All right, so that's -4 u to the 1/2. And then we'll plug in our u back. So we have -4 times 1 minus x squared to the 1/2 power. And then we have this -8 sine inverse of x. And we can't forget our plus c. So the problem, like really, like the problems, the integral problems themselves, this one was a little bit more in depth, but it's nothing you haven't ever seen before. Just remember this algebra at the beginning, where we can rewrite a problem to make it much easier to solve. So I guess that was something that I've noticed a lot, is algebra is expanding things and looking at things in a different way and rewriting it before we solve the problem is very handy on this test. Any other questions on this before I erase it?
Nope.
All right. So those are the tricky parts about the integrals and derivatives. I guess under the derivatives, just remember the chain rule is there. Don't forget it. And I guess, well, when we're on integrals, we'll cover the definite integral, because it's definite integral with kind of indefinite limits. So, or bounds, I guess you could say. So let's say we have an integral that we want to solve, but one of the bounds is infinite, right?
Okay.
It wants us to go to infinity, right? So let's do a simple function, 1 over x, all right? Well, what do we do with this infinity? It's kind of a weird thing, right? So we're just going to take the limit. We're going to actually replace this with a variable, and we're going to say that the limit as it approaches infinity, because you can't really plug in infinity in anything. It's as it goes to infinity. That's how it behaves, right? So we'll say as a approaches infinity, that's an 8. I will make it an infinity of, all right, and then we can solve this real quick. So ln of x, right, as it goes from 1 to infinity. And so we can say the ln of, or this is actually a, and this is a limit. So this limit carries down. So limit as a approaches infinity of ln a minus ln 1. That makes sense what we're doing here?
Okay.
And so now we can just act, so as a approaches infinity, ln also, this part will approach infinity, right? So then that's infinity minus 0, which is equal to infinity, right? So in this particular case, and it kind of makes sense, because if you think about it, well, the bounds are infinite, right? It's just gonna go and go and go and go, but that's not always the case, right? So if we take a look at the graph of ln real quick, that's what the graph of ln looks like. And if we're going from 1, which is right here, to infinity, right? So everything, it's gonna get larger and larger and larger and larger as we continue to extend our x bound. But if let's look at another function real quick. Let's say that this is squared. So we're essentially going to do the same thing that we did before, and we're going to take the limit as a approaches infinity, and this would be a. But now this integral is a little different, right? So this is u to the negative, or x. We don't have to change it to u. So this is x to the negative 2. So it's x to the negative 1 over negative 1, right?
Mm-hmm.
So that's negative 1 over x from 1 to a, and that's a limit as a approaches infinity. So if we plug it in here, so we have my 1 over a minus a negative 1 over 1, right? Well, what happens when we have the limit as a approaches infinity?
That's going to be going towards 0.
So this, yeah, so this just ends up being a 0, right?
Plus 1.
Well, plus 1 equals 1. Well, now our limit is 1, but
Right.
yet, and if we take a look at this graph for a second, it looks something like this. And if we start at 1, which is something around here, I think, and if we go this way, eventually it's never going to go past 1. Does that make sense?
Yeah.
Yeah. It's kind of like the joke about mathematicians going into a bar and ordering a half-size beer every time. It's never going to exceed a certain point. If they each half their order in half, it's never going to get past a certain point. They're going to be an infinite number, but it's never going to pass this one. So it's, yeah. So this makes sense?
Yeah. Yeah, that makes sense.
All right. So there's a definite integral on there that's like that. Actually, one other thing, so if it's like the second one we did, and there is an actual limit, they call that convergent. And if it goes to infinity, it's divergent. So convergent means it kind of has an end. Divergent means it doesn't, it just gets farther apart. I guess next would be a related rates problem. And so I don't feel like there's much different about this problem the problem, the related problem on this test and the stuff that's been on the other tests. So I'm just inclined to redo our cone problem because one can never practice it too much. Yeah. All right. So let's say we have a cone, right?
Right.
Let's fill it with sand, not water. We'll say it's 8 feet by 6 feet. We're filling it at 3 cubic feet a minute. So that's our volume. That's how our volume is changing. And let's say we want to know let's say at the height of 3 feet, how fast is our height going, or how fast are we filling up with sand? All right. And so once again, we're gonna have to do kind of like the triangle relation thing, right?
Right.
And this would be 8 and 6, or not 6. That will be a 3 because it's the radius. And this will be R and H, right? So R over H equals 3 over 8. So
H.
and we want H's, right? Because that's what we want, right? So we want to make sure we replace all our H's or our R's. So we'll say that R is equal to 3, 8 H. And now we can go to our volume equation and rewrite our problem, right? So we have our volume, and so that would be pi times 3 over 8 H squared times H over 3. So that would be 9 over 64, right? And we can actually factor out a 3 here. All right, so that's kind of our new volume equation. All right, and now we can take the derivative of this, right? So that would be 9 pi over 64 H squared, right? And then we got to remember that H is dependent upon time, just as our volume is, so we're going to end up with our dH dt on the end. And now we can plug in our numbers and solve for dH dt. So H is 3, right? So we have 3 times another 9. And we can plug that into our calculator. And I get something like 0.75 feet a minute. Let's specify that this is cubic. Yeah, we did. It's in a minute. So like already. So once you like understand it, it's not like super hard. I know we've done this problem in the past just with different numbers, but I guess things to remember that this R and H are both dependent upon time as well as our volume. And to don't on stuff like this where everything is dependent, don't plug in your variables until after you've solved the derivative.
Okay.
Yeah. So I guess any questions on this?
No, I think that's pretty clear.
All right, yeah. A cone is always a cone, even if it's upside down. That's a hint. Yeah, all right. So,
but wouldn't that be, no, okay.
Yeah.
How would you be filling it though? That's the question.
Sand. Because if you think about it, if we fill the cone with sand, if we fill it with water, water is finite, so it would just fill up. If we fill it with sand, it would build this pile in there. So
I guess it really doesn't change our starting point. It just flips our picture upside down.
Yeah, but if all right, so yeah, so that's our related rates problem. So now delta epsilon proofs.
Yes.
These are fun.
Yeah, trying to do that on the quiz, I just felt like I was going around in a circle.
Well, it essentially is kind of just going around in a circle. Yeah, it's a proof, and you're proving a limit. So let's say we have like a limit as 2x minus 1 as x approaches 3. We know that this limit's going to be equal to 5, right? It's
Right.
pretty easy to see, right? But how do we prove this? Because a limit isn't like a function. So we kind of treat it like a function. We just plug 3 in and we get out a number, right? But a limit really cares about what's happening on either side of the function or on either side of the point, not really what's happening at the point. Because you can have a hole in a graph with a limit still existing at that point, right?
Right.
So that's kind of where the challenge comes in, is how do you prove that as the function gets closer to that point, that's the actual limit. Does that make sense what I'm saying?
Mm-hmm.
So they wrote out a pretty long, complicated process to prove that. But essentially they're going to say, or what they have. So if we graph this, right, so we start at -1, and we go up 2, all right, so we're going to have something that looks like this. Sorry, very not to scale. I'm bad at this kind of stuff. But essentially they're going to say, we're going to have this delta, which is a little change in x. They're going to say we're going to go delta to the right and delta to the left of our point at 3. So they're basically going to set up these bounds. And then they're also going to do the same thing with epsilon. They're going to say, oh, we're going to find our 5, right? And we're going to go a little bit, we're going to make these intervals, and this is the epsilon, right? And we're going to go epsilon up and epsilon down. And we're basically going to build this box around our point. So if we have a point right here, they're going to build a box around it, essentially. And we're going to say that if we have a point here, that it's going to correspond to a point and the y value that's going to be within epsilon of the actual thing. Does it make sense how it proves it?
Mm-hmm.
So it's saying that if we have this x value, it's going to be within so much of the actual point that we want, of this actual value. And so as we get closer and closer and closer, we can prove that it gets closer to 5. And they just write it really weird. Yeah. I guess it's not weird. It's probably it's the proper way. If you understood it, it makes sense, right? But they always start it with kind of the same phrase. So it says for every, I think epsilon? Yeah, epsilon greater than 0, there exists a delta greater than 0 such that
Greater or less than?
Go great. I wrote it back. There we go. You got me. But my writing slants as I get farther away from my body. My arm can't be that far. Yeah. All right. So such that the function minus the limit is less than epsilon when and then it's the value that we're approaching is less than delta. So essentially what this is doing is this is setting up the bounds that we're going to work with, if that makes sense. So that's what these functions are describing, that there's going to be a little bit in each direction that we're going to work with. And now, so they actually use weird notation. I don't know if you've talked about this before, but they replace all this stuff all these words with symbols. And so for every is an upside down A. I don't know why they chose that. And there exists is a backwards capital E. They probably actually have real names. Such that I'll keep it such that delta is greater than 0. And such that is kind of a backwards, it's probably got some Greek name, but such that. And when is kind of this double arrow equal sign.
Mm.
So now, this is kind of our opening statement. And now we're going to go do some math that relates how our delta and our epsilon are related to each other. And so we start off with this. So when we rewrite this, so our limit is 5, right? So we're going to have a function 2x minus 1 minus 5. It would actually probably be good if we, since we are starting with this, we could probably actually just put this in right here. And same thing with here. So the A just talks about this number right here. So this would be a 3. So I think if you were actually writing it out, this is what it should look like. And then they do this. So they always make sure that they're going to relate it back to each other. Right? And essentially, we're going to try to relate these two. And so we can rewrite this as, and we can pull a 2 out, right? And these will all have this when statement. And it's essentially the same. And now we can divide this 2 across. And we have this x minus 3 epsilon over 2. And now if we look at them, we have some similarities, right?
Right.
And so we're just going to replace this with delta. So we're going to have delta is less than epsilon over 2. And that's basically relating our intervals. So that's delta is going to be kind of within this of our limit 5. So that's where this 5 comes in play. That's why it's there. It's because we got to specify that this is where we're starting. And this is why we have a 3 here, because it's specifying we're starting at 3, right? And so once we have this, once we come up with this relation right here, we then go into, well, I guess, our closing statement. And I don't know. So it's kind of just, so it just starts with, so let our delta be less than or equal to our epsilon, or our thing, saying that for every, if we go a little bit this way, we're going to be within that on the epsilon. And then for every, can you still see that? Yep. X within delta interval around 3, because that's where we are, right? It will produce a y value in the epsilon interval around, can't spell, 5, right? So it's basically saying that for every x value, if we take an x value within this interval, we're going to get a y value within this interval. And so, and then it says, therefore, the limit as x approaches 3 is equal to 5. I don't know how well I explain that. Does it make sense? Kind of everything that we've talked about.
The math portion makes sense.
Yeah. So I don't know if it's 100% important to understand this all the way right now. I'm not sure when you would ever use this again, but at least for the test wise, it's in like they'll just be looking for like proper notation maybe, and making sure you have all the steps written out. So I wouldn't worry so much about understanding it, but at least knowing what it should look like, if that makes sense. Because it really is. So I feel like I still have some understanding to work through on this, but it's essentially saying, we're just essentially saying that, like I said at the beginning, that to prove a limit, we have to prove that as it comes from both sides, it's close to 5. We can't just say that this is equal to 5. And this is how they decided to show that. But I guess if you're really smart, it makes sense. I don't know. But so I guess, is there anything you really want to talk about or anything that's really confusing you about this or something?
No, yeah, the process itself seems simple enough. It's just making sure get everything down.
Yeah, so I guess when I took this class, my teacher just said, make sure you get this opening statement and closing statement pretty spot on, pretty verbatim almost, and you should be fine. All right.
Yeah, that makes sense. Once you have that opening statement, if you have it right, it sets you up.
Mm-hmm. All right. So after the epsilon delta proof, there's a continuity problem. It wants to know if a function is continuous. And so quickly for that, just a quick review about continuity. So if a limit as x approaches a of a function is equal to our function at a, then the function is continuous. That makes sense? So, right. Yeah. So that's basically what is going to be talked about. I don't think like the problem is super hard, but just saying that if the limit at this point is equal to the function at that same point, then it's going to be continuous. And I don't know. So I guess we could do pretty much a simple problem. So if we had like 2x plus 3, right, is equal to f of x. And we take the limit as, let's say, x approaches 4. We already know that this is going to be continuous, right, because it's just a straight line. But if we wanted to say that it mathematically, then we can say the limit of 2x plus 3 as x approaches 4 is going to be 8, 11, right? Mm-hmm. And if we plug it into the function, so if the function of 4 of this is going to also equal 11, because we plug in 4 here, 8 plus 3 is 11, right? And so these are the same, so it's continuous. I guess it becomes...
Isn't that silly, though? Because we're literally just plugging the 4 in,
yeah,
and then we're plugging the 4 in again.
Yeah, it's really silly. I guess the thing that makes sense for is when we're working with stuff like piecewise functions. So let's say we have the same function, but this is only for let's say, greater than 4. So for x is greater than 4, right? But then let's say it's like negative 2x plus 7 for any x, or any x less than 4, works less than or equal to, works for here. But anything greater than 4 is now a different function, right?
Okay.
So if we wanted to, we could graph this one and find out if it's continuous, right? We could just plot it out and graph it. And if there's a break in the graph, well, it's not continuous. Or we can talk about the limits, right? So the limit, so this is going to be kind of approaching from the left side, right? And this is going to be approaching from the right side. So the limit as x approaches 4 from the left side of 2x plus 3 is equal to 11, right?
Mm-hmm.
How about this one, though? If the limit as x approaches 4 from the positive side, what do we have?
We got 1 or negative 1.
So there's not even a limit there, right? So can it be continuous? No, right? So does that make sense? So we just, without having to graph this equation, we showed that it cannot be continuous because there's not even a limit at that point. Does that make sense?
Yeah, that makes sense.
So like on this one, it would be pretty easy to graph, right? Because the functions are pretty simple, but sometimes you can have piecewise functions with some pretty complicated functions on there. And then this becomes super handy to be able to do, because then you don't have to sit there and come up with this whole table to graph this big problem, but you can do some algebra and math to calculus to come up with these limits and come up with functions. So and in a case like this one, and this simple problem, I don't think it matters a whole lot. And stuff like this, it probably matters a little bit more. But on complicated problems, it would help out a lot.
Okay.
All right.
Awesome.
All right. So yes. So there are some limit problems on this test.
Mm-hmm.
And I guess limit problems are never like crazy hard, but they can't, so they're a little bit more complicated than beforehand. And so one of the things, all right, so let's talk about limit as x approaches 0 of sinh. All right. So this is equal to 0, right? But I guess the way that you get this, you kind of have to rewrite our sinh to be e to the x minus e to the negative x over 2, because that's what sinh is.
Right.
And then if we plug in 0, we can see that we get 1 minus 1 over 2 is equal to 0, right?
Right.
So I guess that is something that I noticed rewriting these sinh. And I guess cosh is equal to the e to the x plus e to the negative x.
Right. So if it was cosh, then it'd be 1.
Yeah, if it was cosh, then this would come out to be 1, right?
Okay.
So that would kind of be helpful on the limits. The Hopital's rule, if we have infinity over infinity or 0 over 0, how we can take the derivatives of both the top and the bottom. I didn't really have time to come up with an example problem for that one, but
Now, when we take the derivative of the top and bottom, are we doing like literally just the derivative of the top and then the derivative of the bottom, as opposed to if we were trying to take the derivative of the whole?
yeah. So we can actually make this simple. So if we plug in infinity in here, we get infinity over infinity, right?
Right.
So we're going to take the derivative of the top over the derivative of the bottom.
4/3.
Well, there's our answer, right? So
Okay.
yeah. So that's helpful. So that's if you have like infinity over infinity or 0 over 0. or like infinity over 0 or something. Just it doesn't work.
Okay.
And one other thing to check. So let's go back to this problem, right? So we know that the graph of this looks like this, right? And as x approaches 0, right, this is going to be a smaller and smaller and smaller and smaller number, right?
Mm-hmm.
Which makes this is basically going to come out to be infinity, right?
Great.
But so on this problem, it doesn't matter a whole lot, but sometimes our problems will have different sides. So like if our problem looked like, if a graph looked like that,
Mm-hmm.
and we're taking the limit as at 0, if we're coming from the left side, it's going to be negative infinity, right?
Mm-hmm.
If we're coming from the right side, it's going to be positive infinity. If we had something that looked like this. And in this case, the limit doesn't exist. If in this case, the limit does exist, because if you're going from both the left and the right, you get infinity, right? But just double check when you're doing your limit problems. That might save you a point or two. Just make sure you double check all your stuff. Go from the left and the right.
Okay.
And so that's limits. Any other questions about limits?
Mm-mm.
All right, so then I guess there's one other thing to cover. So definitions of derivatives and the quotient difference. So the quotient difference is difference quotient. Got this backwards. This f of x plus h minus f of x all over h. This is called the difference quotient. And it's just basically saying that we have this function, we're going up a little bit, and we're minusing the original function divided by the amount we went up. And essentially, like this is the little bits of change we're doing. So when we take the limit of the difference quotient as h approaches 0, whereas the amount we're changing gets smaller and smaller and smaller, this is a derivative. And people were really smart and came out with a bunch of rules that help us simplify it. But we can use this to find all sorts of derivatives, right? It's just a bunch of algebra. So let's say we had right. If we want to take the derivative of this would be pretty easy, right?
Right.
It's just 2x plus 6. But if we wanted to prove that was the derivative, we could do this. We could find the difference quotient and take the limit as h approaches 0, right? So we're just gonna take this function and plug every instance of h for x plus h. So we're gonna have x plus h squared plus 6 times x plus h. And then we're gonna minus our original function. We're gonna all divide that by h. But then we're gonna take the limit as h approaches 0. Or we're gonna say the amount that we're changing is gonna keep shrinking and shrinking and shrinking until we're basically doing little teeny tiny amounts.
Okay.
And now if we just take the limit here, right? If we put in a 0 on the bottom, it doesn't work. So we gotta get rid of this h. So we're just gonna do some algebra, and we're gonna get x squared plus 2xh plus h squared plus 6x plus 6h minus x squared minus 6x. Some big log algebra thing all over h. Then we're just going to cancel like terms, right? Because this x squared minus x squared disappears. 6 plus 6x minus 6x. And can we cancel anything out? Not really. I don't think so. So we have 2xh plus h squared plus 6h all over h, right? And now we can factor out an h, right? Because they're all multiplied by h. So
and now we plug in the 0.
So we can take the h out.
After we take it out, yeah.
Yeah, because these h's will cancel, and we plug in the 0, the limit for h, and that is equal to 2x plus 6.
That's a much nicer proof than the epsilon delta.
Yeah. The epsilon delta makes sense to some people, I'm sure, but yeah. So I guess you can't really see my last stuff over here, but you end up with the same thing as 2x plus 6 as our answer. So, and the way it goes, it's like they're not hard problems per se, but it's just remembering that there's a limit and canceling out all our junk. And you can always check your work on this particular stuff, because if you look at this function, we know what the derivative is supposed to be, right? We can just take it. So more complicated problems, if this was more complicated, we could take the derivative of it and then say, well, I know what my answer is supposed to be, right? And then you can just double check our work.
Make sure you got it. Okay.
Yeah. So I guess that's pretty much it. I guess, is there anything else that you would want to cover, or anything else that we didn't cover that?
Let me just double check the study guide just to make sure. All right. So we have that. Find a limit. Would you mind just, you don't necessarily have to walk me through, but just refresh me on, for an initial value problem, are we taking the integral, or are we taking the derivative of the function that they give us?
Oh yeah, I forgot that initial value problem, man. So initial value problem is an integral problem.
Okay, got it.
So I guess I could come up with something. So let's say we have a velocity, all right? Say we're going like 12 feet a second, right? That's our velocity, right? So this would be a very simple one, but then let's say our position at, let's say time, our position at time 0 is equal to 100. What's our position function? So if we had something that said something like this, what's our position function? Well, we know that velocity, the integral of velocity is position, right? So we're just going to take this integral of this 12, and we're going to get 12t, right? Plus c is equal to position with respect to time. And then we use our initial value point. So we know that when t equals 0, our answer, or our position, is at 100 feet, say. And so now we know what our c is, right?
Right.
And then we can replug this c back into our equation and come up with the actual position function.
Okay.
If we wanted to take it one step farther, we could say, how long will it take for us to get to 1,000 feet, right?
Right, and then that's just simple.
Yeah, 1,000 equals.
Plug it in.
Yeah, and so it'd be 900 divided by 12, right?
Okay.
So that's how long it would take. It's correct. It's just not simplified. Yeah. So initial value problems, they start you with some equation, and you're taking the integral of it to find kind of an original equation. So
Okay. Initial value, limits, continuous, piecewise function. Okay, awesome. Find
Well,
two improper integrals.
that was the definite integral with indefinite bounds.
Oh, okay.
The improper integral, where you have like the infinite value on one side, and you have to take the limit, and you replace your infinite value with the variable, and you take it as a limit. So, are there any other questions that you have?
No, I think I'm good.
All right. Well, I think that's it then. This test, I feel like the story problems aren't as hard, but there's a lot of harder integrals and derivatives.